to our powers unit review. All right. So we're going to start by looking at question 1. Asks us to describe what each exponent law is saying. So I might say briefly in words what we mean when we say a to the power of m times a to the power of n is equal to a to the power of mn. I might, or m plus n, pardon me. I might say when we multiply powers with the same base, that means the a's are the same, we add the exponents. Now, I'm not sure I'm going to have room necessarily for all of these answers, so I think I'm going to finish A and see what I can do here. So I'm going to do a little line here. All right, and so this one says when we divide powers with the same base, we subtract the exponents. We subtract the exponents. And lastly, if I raise, well, we said we before, if we raise a power to an exponent, we should multiply the exponents. Okay, so I've got a bit of a bread and butter exponent questions here. I'm going to zoom in a little bit so you can see, and I'm going to refocus here. All right, so we're going to take a look at this question here. This asks us to multiply these terms together. So we're going to multiply the values with the same base. We're going to add the exponents. So it's going to become x to the power of 10 times y to the power of 2 plus negative 8. 2 plus negative 8 is negative 6. And then I'm not done until I resolve all my negative exponents. That becomes x to the power of 10 over y raised to the power of 6. And that's my answer. I'll try and write a little bigger so that it's a little more obvious what those numbers are. All right. With a question like this, I need all of my powers with the same basis to communicate. So I'm going to have 6 x to the power of 6 take away 1, which is going to be, 6 take away negative 1, which is going to be 6x to the power of 7. Y is going to be to the power of negative 2 take away 2, or negative 4. And z, I'm going to cross my z so it doesn't look like a 2, it's going to be negative 3 take away negative 8, which means negative 3 plus 8, which means z to the power of 5. And that, I got to take my negatives and flip them down to the bottom. It's going to be x to the 7, z to the power of 5, all over y to the power of 4. All right, moving on. We have this negative exponent on the outside of a bracket. Now, depending on what I have on the inside, I may want to flip the inside of the bracket first or not. In this case, I think it's going to be pretty friendly just to multiply this through. So I'm going to see what this looks like. X to the power of negative 6 times y raised to the power of 8. And again, I have to resolve these negative exponents. This guy flips down to the bottom, and I get y raised to the power of 8 over x to the power of 6. Now, in this case, because I have a negative exponent and a fraction on the inside of this bracket, it might be nice to first flip this guy around. So I could say that's equal to y to the power of 5 over x to the power of negative 3. That's all squared, which is to say it's all multiplied by itself. So I could say that when I have this situation, I can multiply this exponent in. I get y to the power of 10 over x to the power of negative 6. Now again, I have to resolve these negative exponents. I could have done this earlier, actually, and maybe I should have. I should have maybe done my bracket step first. Nonetheless, I'm going to flip it up to the top and change this to a positive 6. And I like to write my variables in alphabetic order. So I get x raised to exponent 6, y raised to exponent 10. All right, moving on. Okay, so I'm going to do the things on the top of the bracket first. So x cubed times x to the power of negative 2 becomes x to the power of 3 plus negative 2, or x to the power of 1. and then y to the power of 4 plus 4, or 8, over x to the power of 4, y to the power of 10. And I do a subtraction here, 1 take away 4, so I get x is power of negative 3, and y is raised to the power of negative 2. And I should flip both of these under 1, which gives me 1 over x cubed y squared. Okay. A lot of things happening here. I'm going to start with the exponent step. And you know what? I'm going to do the exponent step here by itself. So I'm going to say a raised to the power of 9, b raised to the power of 6. And I'll keep that instead of brackets. And maybe, since these guys aren't going to do anything, maybe I can at least multiply these together. So I'm going to group those together. So I've got a raised to the negative 4, b to the power of 1 plus 6, so that's b to the power of 7, c to the power of 1 plus 2, which is c to the power of 3. And then I got I'll multiply these all together. I'm going to add exponents. A to the power of 9 plus a to the power of negative 4 is a to the power of 5. B to the power of 13, c cubed. And that's it, actually. I'm done. All right, a bit of a larger question here, question G. Again, I'll start with my exponents on the top, and I'll do a multiplication on the bottom. So I've got a to the power of 4 times 3, or a to the power of 12. B to the power of 5 times 2, which is 15. And that's all over a to the power of 2 plus 6, or 8. And b to the power of 3 plus 12, or 15. All right, so I should subtract when I divide my powers with the same base. So a is going to be raised to the power of 12, take away 8, which is 4. And b is going to be raised to the power of 15, take away 15, which is 0, which is the same thing as saying a to the power of 4, because b to the power of 0 is 1. Last step. I've got a cubed b, and I'm going to multiply this by, I've got a negative exponent and a fraction on the inside of a bracket. So I'm going to flip that fraction first, a squared over b raised to the power of 4. And that's actually all squared. I should probably square that next. So that's going to look like a cubed b times a squared is a raised to the power of 4. A squared squared is a to the power of 4. And a b raised to the power of 4 squared is b to the power of 8. And that's a fraction. I'm going to multiply them together. So this is a fraction as well. I'll multiply across the top. So I've got a to the power of 7 over times b over b to the power of 8. And then I can subtract these exponents if I want. There is a faster way, though. I know that this represents 1b on the top, and that represents 8 b's multiplied together on the bottom. So I can imagine dividing the top and the bottom by b. And that changes this exponent to a 7. So I get a raised to the power of 7 over b raised to the power of 7. Now, you might have gone a different method there. You might have subtracted, got b to the power of negative 7 on the top, then flipped it down here. Either way is fine. Okay. So moving on to question 3. So we're going to evaluate some expressions here without variables, instead with numbers. So first is a pretty straightforward application of our exponent law. We're going to write this as 1 over 3 with a positive exponent squared. And I'm going to go one step further and say 3 squared is 9. 5 raised to the power of 0. Anything to the power of 0 is just 1. So that's nice and easy. All right. 1/2 raised to the power of negative 4 is the same thing as 2 over 1 raised to the power of 4, which is the same thing as saying 2 to the power of 4. And that's 2 times 2 times 2 times 2. And if that's confusing to think about, I can think that's 4 times 4, which is 16. Next, 3 to the power of 0 is 1, and 4 to the power of 0 is 1, 5 to the power of 0 is 1. So together, these give us the value 3. Similar to this step, I'm going to say, okay, that's 5/2 raised to the power of 2. So that gives me 25 when I square them over 4. This is the final answer. Anything raised to the power of 0 is just 1. Okay, so this is going to be a little bit more tricky. So you might want to do some exponent laws here, but we don't have a rule for when you have the same base and you're adding exponents. We don't have a nice rule anyway. All right, so we're going to have to go around this a long way. So 4 raised to the power of negative 1 is 1 over 4 to the power of 1, which is just 1 over 4. And 1 over 4 raised to the power of negative, 4 raised to the power of negative 2 is 1 over 4 squared. So that's another way of saying a quarter plus a 16th. Now, if I want to add fractions, I have to have common denominators. So I'm going to multiply this one by 4 and 4. That's going to give me 4 sixteenths plus 1 16th, which gives me 5 sixteenths as a final answer. And lastly, I have 8. So same base, I'm going to add the exponents. Negative 4 and 4 give me 0, which is anything to the power of 0 is 1. All right. So moving on, we've seen a few of these questions before. Let's go over the first one. So what power could I raise x to get this fraction? Well, if I'm not sure, I might try some powers of 3. Say 2. Does 2 work? Well, 3 squared is actually 9. So that's no good. It's too big. Bigger than 1 over 81. So I'm going to try a smaller exponent. 3 to the power of 1. Well, that's 3 is still too big. What about 3 to the power of 0? Well, I know that's 1. So that's even 0 isn't small enough to get this fraction. So maybe I should try a smaller value even. 3 raised to the power of negative 1. Well, that's going to be 1/3 to the power of 1. Okay, so still not small enough because 1/81th is a very small number. So I'm going to say, okay, what about 3 raised to the power of negative 2? Well, no, that's 1 over 3 to the power of 2, or 1 over 9. 3 to the power of negative 3, maybe that's it. And I get 1 over 3 cubed. But 3 cubed is 3 times 3, or 9, times another 3. So it's not that one either. So 3 to the power of negative 4, maybe? So it's going to be 1 over 3 raised to the power of 4. And 3 to the power of 4 is 81. So x equals negative 4. And I can check that value by punching it back into the calculator. All right, for this one, I'm going to start by saying this looks complicated, so I'm going to simplify it. I'm going to say let u equal 3x take away 8. I'm going to rewrite the expression. 5 to the power of u equals 1/5. Okay. Now, if I can think, well, what power could go here to rewrite it as a 1 over 5? Actually, I can see that that's going to be 5 to the power of negative 1 is 1/5. So u is negative 1. But I wasn't asked for u. I was asked for x. And so I need to go back to my original statement and say, okay, well, if negative 1 is equal to 3x minus 8, maybe I can find x. To do that, I'll add 8 to both sides. And I get 3x on the right and 7 on the left. Divide by 3 on both sides. And I get x is actually 7/3, which is a pretty hard number to have just guessed and checked. Oops, I realized I was writing off the screen there, but only for a step, I suppose. And we get 7/3 as a value, as an answer. All right, moving on. So for the numbers 234 and 300, we're going to find the greatest common factor and the least common multiple. To do this, I'm going to start by doing a factor tree of 234. I don't know any factors, but I know it's even, so we can start there at least. 2 and I guess I get 100 is half of 2. Half of 34 is 17, which kind of looks primey. Maybe it's a prime number. But then I look and I say, okay, I know this trick. If I add 1 plus 1 plus 7, I get 9. 9 is divisible by 3, so this can be divided by 3. That means, okay, I can see it now, because 120 is 3/40s, so this must be 3/39s. 39 also is divisible by 3. I get 13, and then we're done with our prime factorization. 234 is really 2 times 3 squared times 13, or 2 times 3 times 3 times 13. And depending on what we're doing, it may be easier to write our factors like this, or like this. All right, we're going to do the same thing for 300. All right, so that's 103. And so your prime factorization may look different. Let's say we'll go 4 and 25. And 4 is 2 and 2. And 25 is 5 and 5. So 300 is 2 times 2 times 3 times 5 times 5. Or, in other words, 500 is 2 squared times 3 times 5 squared. Okay, so the GCF, well, to find the GCF, I'm going to use a highlighter here. Oh man, I had that all off the screen, didn't I? What a guy. I do apologize. All right, so to find the GCF, I'm going to find the common factors. Looks like there's a 2 common between both of them. There's a 3 common between both. And that's it looks like. So the common factor is 2 times 3, which is 6. The greatest common factor between 234 and 300 is the number 6. All right, to find the LCM, I'm going to write each of the primes that show up in either prime factorization. So it's 2, 3, 5, and a 13. I'm going to write down the highest power, so I'll use a different color highlighter here to decide on those. So, okay, so I've got a 2 there, 2, and a 2, and a 1. Okay, so the highest power on 2 should be the 2 from 300. Highest power on 3 should be the raised to a power of 2 from 234. 5 should also be raised to a power of 2, and then times 13. So the LCM is going to be quite big. It's going to be 4 times 3 squared is 9. It's 25. 5 times 5 is 25 times 13. Okay, so that means it's going to be 36 times 25 times 13. And we've got to a stage where I can't do that in my head anymore. So I'm going to pull out the calculator. 36 times 25 times 13. And that gives a big old number of 11,700. Okay. Next, so we've got a question that asks, well, we've got some prime numbers here, P1, P2, and P3. And these are the prime factorizations of A and B. So can we find the GCF? Well, to find the GCF, we're going to say, well, what are all of the prime factorizations, prime factors that are present in both of these factorizations? Well, it looks like at least one P1 is in each of them. But I think maybe it's easier for me to visualize it by writing it out. P1 times P1 times P1 times P1 times P1 times P2 times P2. And this one is P1, A equals, times P2 times P2 times P2 times P2 times P3 times P3. And for me, that's a little easier. So I'm going to go highlighter route. I'm going to say I can see one P1 in both. So I'm going to write a P1 here. I can see 2 P2s that are common as well. So I'm going to write 2 P2s. I'm going to write this as 1 like that. Okay. And so that's my GCF right there. My GCF is P1 times P2 raised to the power of 2. My LCM. Okay, so here I'm going to list each of the primes that show up in either of these factorizations. So P1, P2, and P3. And I'm going to write the highest power that shows up for each of them. So highest power of P1 is 6. Highest power of P2 is 4. And highest power of P2 is 3. So my highest power on P1 is 6. For 2, the highest power is 4, and then for P3, the highest power is 2. I'm going to underline those in yellow as well, so we can see where those numbers came from. All right, those are our answers. All right, is it possible for two numbers to have a greatest common factor of 24 and a least common multiple of 150? And we'll have to give some justification for why or why not. All right. Well, I think in order to do this, I'm going to want to take a look at the prime factorization. So I'm going to split 24 into 12 and 2. 12 splits into 6 and 2. And 6 splits into 3 and 2. So that means 24 is really 2 times 2 times 2 times 3. or 2 cubed times 3. And 150 is 50 times 3, and 50 is 25 times 2. 25 is 5 times 5. Okay, so that means 150 is the same thing as 2 times 3 times 5 times 5, or 2 times 3 times 5 squared. Fine. Okay. So is it possible for two numbers, let's have the greatest common factor be 24, and least common factor be 150. Okay, well, let's think about that for a second. Let's start with the greatest common factor. Okay. If I knew that this was the greatest common factor of two numbers, call them A and B, number A, would have to at least have shared this many factors, and maybe has others, with B. And that's what a greatest common factor is. 2 times 2 times 2 times 3 times dot 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 dot. So they would have at least had to have shared these values. They would have to be the same. And that's what the greatest common factor is. They share a certain number of prime factors. Okay, so that's fine. Now, if that's true, is it possible that the LCM of these numbers even, imagine we forget any of the other, imagine we forget any of the other factors. Well, the LCM of these two numbers would at least have to have a 2 raised to a power of 3, at least. Maybe they have more powers of 2, or pardon me, more factors of 2 somewhere else. Now, because there's no raised to a power of 3 above the 2, we can say that no, this is not possible. So I'm going to say that in words. No. This is not possible because any two numbers with a GCF of 24 must have 3, it must have 2 cubed in their prime factorization. Now, if it's true that they had 2 cubed in the prime factorization, then since the LCM of 150 didn't have at least a power exponent of 3 on the factor 2, the factor 2, since the LCM 150 didn't have a lead, the 150 is not the LCM of number A and number B. Okay, and that's our review package. Please let me know if you have any questions, and you can stay after school on Thursday to get any extra help.